Well, welcome to the next topic, which is on chemical bonding. Now, in my class, I split this up into 2 days: 6.02 ionic bonding and 6.03 covalent bonding. But I'm going to do this all in one go because it's all in one PowerPoint. So if at any point you feel you need to stop, then stop. But you might want to keep going. This is going to be fun. Now, we've taken a look at atoms. This entire course so far has really been a look at atoms, what atoms are made of, and stuff like that. But we really haven't talked at all about how atoms will stick together. Yeah, we briefly mentioned it, but we really haven't gotten into any kind of detail. So, how exactly do atoms stick together to form compounds? That's what this is going to address. Chemical bonds involve valence electrons. These are the ones in the outermost energy level. Atoms can either lose, gain, or share however many electrons are necessary to form a stable octet. Now, this is only going to be for elements in groups 1 and 2, and then in groups 13 through 18. The transition metals are a lot more complicated, so we're going to be leaving that out of what I'm going to show you here today. Any chemical energy that a compound actually has, like imagine dynamite or nitroglycerin or even gasoline, all that energy is stored in those chemical bonds. When you break a bond, it requires you to put energy into it in order to get the bond to break. Like if you wanted to break a pencil, you'd have to put energy into the pencil to break it. And when new bonds form, that releases energy. We're going to do an entire topic later in the year on this energy absorption and release, exothermic and endothermic. Now, electronegativity, as we said, is an atom's attraction to electrons. So, bonding is a competition for electrons. What an atom does with its valence electrons will depend on the difference in the electronegativity between the atoms that are bonding together. Now, in New York State, you have use of reference table S to look up the electronegativities of atoms. The electronegativity difference, which we will henceforth abbreviate END, is the higher electronegativity minus the lower electronegativity. That way there's no negative numbers. If the difference is 1.7 or higher, that means that the pull on electrons is different enough that one atom is able to successfully remove electrons from the other. This will result in a transfer of electrons from the atom with lower electronegativity to the atom with higher electronegativity. If the electronegativity difference is less than 1.7, then the difference isn't strong enough to result in a transfer. So electrons will be shared to form covalent bonds. There is one exception to this. There is one bond with an electronegativity difference of 1.8, and it's between the two nonmetals, hydrogen and fluorine. That would still be considered a covalent bond. Now, this is a very oversimplified explanation. If you continue on and take higher level chemistry, you'll learn about something called net ionic character, but we are not going to get into this in this particular topic. So let's start off with ionic bonds. The metal atom is going to have very low electronegativity, and it will lose all of its valence electrons, leaving the shell underneath with a stable octet. And the metal atom becomes a metal ion. It's positively charged, and we call that a cation. The nonmetal atom with the higher electronegativity, the stronger pull on electrons, will gain the electrons from the metal, and it will gain enough to form a stable octet of its own. And since negative electrons were gained, it will form a negative ion, which we call anion. And what happens is, once the ions form, since they're oppositely charged, they will attract each other. And that attraction is the ionic bond. And it's only a surface attraction. It's actually not that hard to break. All you have to do is either add enough heat to break it, and ionic compounds tend to have pretty high melting points, Or you can dissolve it in water, and the water molecules will go in and pull the ions apart. We're going to do an entire unit on how the dissolving process works. Under both conditions, since we have loose ions that are able to move, these charged particles in motion are capable of carrying electric charge. When you dissolve an ionic compound in water, the resulting solution is called an electrolyte, which is a term you will hear several times as we go throughout the course. So, an example of ionic bonding, one that you may be very familiar with, we're going to start with sodium and we're going to bond it with chlorine to make sodium chloride. You'll notice that sodium has an electronegativity of zero point 0.9, verifiable through reference table S. Chlorine has an electronegativity of 3.2. So let's take the difference between them. We subtract the lower one from the higher one, and our difference is well above 1.7. That means chlorine has enough energy, enough pull on electrons to completely remove sodium's one and only valence electron. And look what's going to happen. Sodium only has one electron to lose. Chlorine only needs one more to gain. So the electron will transfer from the sodium to the chlorine. Let's see how this looks with dot diagrams. All right, sodium, cough up that electron. There you go. Sodium now no longer has one valence electron. Now it has the 8 electrons underneath. Chlorine no longer, and its ion charge becomes +1. The chlorine will go from having 7 valence electrons to having 8 valence electrons and result in an ion charge of -1. And this is how we would draw the dot diagram for the ionic compound sodium chloride. The ions in their brackets, the metal with no dots, the nonmetal with 8 dots, and the ion charges on the upper right side outside the brackets. Let's do some more examples after a quick animation. So the blue represents the electron cloud of the atom, and you'll notice how chlorine removes the electron from sodium, and then the oppositely charged ions will attract together, and this forms a crystal lattice of salt. Scale this up, and you'll actually be able to see it. Put it in your mouth and say, "Huh, it's salty." Here's another example of ionic bonding, potassium and oxygen. You'll notice potassium has only one electron to lose, but oxygen needs 2 more electrons to make a stable octet. If we take the difference between their electronegativities, once again, that's well above 1.7, which means oxygen has more than enough power to take potassium's electron from it. Now, because oxygen needs 2 more electrons, but each potassium can only provide 1, we're going to require 2 potassium atoms to make oxygen whole. So the potassiums will lose their electrons to the oxygen. They will lose their valence electron. You'll notice now it's just 2-8-8, and it now has a +1 charge. The oxygen was 2-6, and now it's 2-8, giving it a -2 charge. We put the negative ion in between the 2 positive ions because positive ions would repel each other, but they're both attracted to the negative oxide ion that you've just formed. So, that is ionic bonding. Relatively straightforward. Covalent bonding is too, although, again, what I'm going to show you is a oversimplification. When you go on to take college chemistry, you're going to learn about sigma bonding, pi bonding, hybridization. I'm going to leave all of that out and just give you the fundamentals of how a covalent bond forms. All nonmetal atoms have relatively high electronegativity. Hydrogen has the lowest at 2.2. Fluorine has the highest at 4.0. If the electronegativity difference is less than 1.7, once again, the exception being HF, it's not enough for the transfer of electrons. The atoms will have to share their unpaired valence electrons in order for stable octets to form. Each shared pair will actually be an overlapping between the two atoms. The two bonded atoms will actually become part of each other. This makes a covalent bond extremely difficult to break, far more difficult than breaking an ionic bond. If you melt a molecular substance, the molecules will separate, but the bonds will remain intact. If you melt an ionic substance, the ionic bonds themselves will break. Each shared pair will combine atomic orbitals to form molecular orbitals. So again, the bonded atoms basically become part of each other. You cannot break a covalent bond by dissolving in water. The one exception to that being acids, and you'll have a whole unit on acids and bases later on. And covalently bonded compounds, with the exception of acids, do not conduct electricity when you dissolve them in water because they do not break up into ions because they're not ionic. Okay, so some examples of covalent bonding. Hydrogen and chlorine, which combine to form hydrogen chloride. Hydrogen has one electron to lose. Chlorine needs to gain one to make a stable octet. So you would think it's no big deal. Chlorine will remove hydrogen's electron, they'll form ions and go about their merry way. But not so fast. Their difference is not high enough to make the bond ionic. The difference is only 1.0, and this is less than the 1.7 threshold for an ionic bond. So chlorine and hydrogen are going to have to compromise. Since chlorine can't just remove hydrogen's electron, they're just going to have to agree to share. And this shared pair of electrons is a covalent bond. It's also referred to as a molecular orbital. You see, this orbital, and this orbital belong only to the chlorine atom. These are atomic orbitals. But these two electrons come from both hydrogen and chlorine. They don't belong to either atom exclusively. They belong to the molecule. So they are a molecular orbital. Chlorine ends up with a stable octet because thanks to hydrogen sharing its one electron, and hydrogen has a completed first energy level. Hydrogen is happy with just 2 electrons. We'll call that a stable duet. Although I don't know if hydrogen sings. Maybe. Here's another example. Hydrogen and oxygen. So hydrogen has 1 electron to lose. Oxygen only needs to gain 2 to make a stable octet. But the difference is not great enough. It's still under 1.7. So oxygen doesn't have enough force to remove hydrogen's electron. So once again, they have to compromise and share. The shared pair of electrons are your covalent bonds. This is an example of a water molecule, and the shape of the molecule is the way it is because of where the unpaired electrons are in the hydrogen atom. Water molecules are bent, and as you'll see in the next unit, this gives water very special properties that most molecules its size don't have. No spoilers. The oxygen has a stable octet thanks to the shared electrons, and the hydrogens have a stable duet, again thanks to oxygen being so willing to share its electrons with it. Here's another example. Hydrogen has 1 electron to lose. Nitrogen needs to gain 3 to make a stable octet. But once again, the difference is not great enough for a transfer of electrons. So they'll have to be satisfied with sharing their unpaired valence electrons. And once the unpaired valence electrons pair up, you'll form covalent bonds. It's kind of like a handshake. A handshake requires each person to kick in a hand to the handshake. Nitrogen has a stable octet thanks to the shared electrons, and hydrogen has a stable duet for the same reason. All right, one more example, hydrogen and carbon. Now, in the last unit, we talked about how carbon has 4 valence electrons and how its electron dot diagram would not allow it to form a stable octet if it bonded as is. So I'm going to show you how that works right now. The difference between carbon and hydrogen is not great enough for the bond to be ionic. Therefore, they're going to share electrons. The problem is carbon, the way it is, can only form 2 bonds. And if it forms 2 bonds, it will only end up with 2, 4, 6 electrons, not a stable octet. So something's going to have to give for carbon. Before carbon can form a bond, this s electron will have to be excited to the next available p orbital. And when that happens, now the carbon will be able to share enough electrons to form a stable octet. So when you draw the dot diagram of carbon for the purposes of bonding, put 1 dot on each side. And then when the bonds form, the carbon will be satisfied with its stable octet. We have 4 pairs of shared electrons, so we have 4 covalent bonds. The carbon is happy with its stable octet, and the hydrogens are happy with their stable duet. And that is the simplified version of ionic and covalent bonding. Now, that is not as far as it goes with covalent bonding. We have something called polarity of bond. See, just because they're sharing electrons doesn't mean they're being shared equally. So, as the difference in electronegativity between the atoms that are bonded increases, the more electronegative side, the one with the greater pull on electrons, will become more negatively charged, while the less electronegative side will become more positively charged. So if there's no difference in electronegativity, then there's no charges. But as you get a difference in electronegativity, you do get a partial separation of charges. Not an ionic separation, but a partial separation. So let's see how that works. Between 0.5 and 1.7 electronegativity difference, the difference in pull between the atoms is strong enough to produce partially separated charges on each end of the bond. The more electronegative atom will be partially negative. That little lowercase delta, the Greek letter delta that you see there, means partial. You may recognize capital delta, the triangle, as meaning change. Lowercase delta means partial. The less electronegative atom, therefore, will become somewhat positive. Not full separation of charges, just partial separation of charges. So let's take a look at an example of this. Okay. So here we have hydrogen and iodine that have a difference in electronegativity. It's not that great, but you're going to see how the electrons are pulled a little more towards iodine than they are to the hydrogen. And this is going to build up a slight separation of charge. That's what polar means, like north and south pole, positive and negative pole. Here's another example. When hydrogen and oxygen form bonds, the oxygen is significantly more electronegative than the hydrogen. So the oxygen will have a very strong partial negative charge. Not fully negative like an ion, but there is a separation of charge that's slight. This separation of charge tends to be much stronger in acids, which is why acids are much more easily able to dissolve in water and break up into ions. But more about that when we deal with the acids unit down the road. So what about nonpolar covalent bonds? Well, if the difference is very small, then there's not enough difference in pull to separate the charges. So there will be no partially charged ends. So in this case, with two atoms of exactly the same electronegativity, they will completely share electrons evenly and no separation of charges will take place. You'll have a non-polar covalent bond. And this happens between an electronegativity of 0 and 0.4. At least that's what New York State Standard specifies. Here's an animation of how atoms bond together. So what happens is we have on the left side a sodium atom and we have a chlorine atom. You'll notice that the sodium has one valence electron, and when it's done forming an ion, it has 8. The chlorine has 7 valence electrons, but once it has gained the one from the sodium, then the chlorine will have a stable octet. Sodium will become positively charged, and the chlorine will become negatively charged, and the two ions will attract. And you'll notice they both have a stable octet. This is what is required. By the way, the X in the dot diagram represents the electron gained from the sodium. Now, here we have a bond between hydrogen and oxygen. But you'll notice that the oxygen isn't completely stealing the electron. It's still sharing electrons with the hydrogen. Hydrogen only has one electron of its own. But the oxygen has 6 electrons of its own. It only needs 2 more. But it doesn't have enough electronegativity to completely remove hydrogen's electron, so they share electrons to form a covalent bond. Since oxygen gets the electron more often than the hydrogen, the oxygen will be partially negative and the hydrogen will be partially positive. This is a polar covalent bond. We'll add a second hydrogen to complete oxygen's stable octet. And then what we're left with is a molecule of water. That is all there is to the periodic table and bonding unit. The next unit is going to be about compounds, and you're going to learn about how to write formulas and names of compounds and some mathematical properties of these compounds. In the unit after that, you're going to learn how to react elements and compounds together to make chemical reactions. And in the unit after that, you're going to learn about the energy that comes out of these reactions and how to change the speed of these reactions. But for now, we are done with Unit 6. Thank you for playing along, and until next time, bye!